The COVID pandemic is truly a life-changing phenomenon, and every major crisis creates an unexpected clarity. Those are words from Francis Wong. The pandemic is giving us the experience of just having enough and still feel truly blessed. It is totally a humbling spiritual practice. Yes, we are not at the monasteries like the monks, the nuns, and the priests, but we can consider that the real world is there for our spiritual practice. We can have the refiner's fire mindset. And yes, everything and everybody in the real world are messengers of God. We can relate to our experience with them by asking ourselves, what message do we have from this encounter, from this experience with them? And from my experience with them, what can I gain that can help me in my quest to holiness? Everything in the real world is affirmation. And yes, we are all called towards being holy and towards becoming saints. So what do monks, nuns, and priests have in common? They live a minimalist life, staying away from the attachments, from that big worldly ego. And yes, being a materialistic or a material being, it's nice to have minimalism as part of our spiritual practice. Yes, we all have our own ego. Now that I'm talking to all of you, I'm giving way to my ego, through my ideas. And yes, if we have a spiritual practice of keeping our ego at a minimum, then we can have more time, more room to listen to God, to the surroundings, and to the people around us, to our family and friends. And yes, we can still appreciate the world without much attachments. When we see the monks, the nuns, and the priests, then we can reflect on our personal attachments. Do we have a lot of them? Are we strongly attached to them? Money, career, success, having many followers, cars, house, to name a few. Then we can go back to our intentions of why we want to acquire some of the material things, why we need the money, why we are doing what we're doing for money. Then we can review the foundations or the principles of the metaphysics of money and always be reminded that God provides what is best for us. Why should I start a spiritual practice of minimalism, for example, as part of our lifestyle? Then we can have more money to save because we have the examples of the monks, priests, and nuns. If they are able to live a meaningful life without not having a lot materially, then we can also do so. Francis Wong shared these messages. We will never change unless we are being challenged. So we can continue to grow by claiming mastery, autonomy, and sense of purpose. So let us continue to claim our identity of being limitless, even if we have a lot of struggles and we just have enough by having our own culture and adventure in enriching our spirituality. Devoting time on mass teaching gives way for authentic knowledge and for me to experience the incarnation of God. Why do math and history draw each one to the incarnation of God? When we study closely history, we will always come across amazing stories about math legends and math scholars who happen to answer our questions that only spirituality and faith can answer. There is indeed God. And yes, because of our curious minds, Christianity flourished. So let us enjoy in this episode a piece of classical math heritage and be united with all of the students of life and believers around the world. Grade 10 Depth and Geometry, gives a wonderful transition towards pre-calculus by introducing slowly the standard form of equations in conic sections. I was wondering, why study the conic sections? Why consider the cone? True enough, the foundations of the studies for the cone and the conic section, it will going to help us in optimizing analytic geometry figures in solving problems like volumes. And then, why is it that we are considering a cone? As you can see, as a geometrical figure, the cone has a circle and a triangle. Hence, if we will apply our knowledge about the unit circle and the triangle and the cone, then we have the basics for the study of good measure. The scope of this math blog as a supplementary learning is to present GeoGebra builds that would illustrate about the concepts of distance formula and some of the standard forms of equations for conic sections. Yes, indeed, the distance formula is just an application of the Pythagorean theorem. Okay, so in this episode, I'm going to present some GeoGebra build that can illustrate the distance formula, the Pythagorean theorem, and later on, we'll consider one standard form of equation in conic section. Okay, so let's start with the GeoGebra build of green maths. Okay, so here in his build, we have a Cartesian plane. Okay, and in the Cartesian plane, we have points A and B. Okay, and since they are in the Cartesian plane, then we can then find the coordinates, right? So show coordinates. Okay, so point A has coordinates x1 labeled as x1 and y1. So A is at point 1, 1 of the Cartesian plane, and we also have point B with coordinates labeled as x2 and y2. Okay, and B is indeed at point 54. Okay. Now, if you were going to recall the foundations of Euclidean geometry, there's a study about right triangles or properties of right triangles. So we can try to see if that distance, if that line can create a right triangle. So we'll do that. And here it is. We already have a triangle, and it's a right triangle. Okay, so the next thing is to find the base and the height of the triangle. So how to do that then? Okay, this build is telling us then that the base is just the change or the difference of the x coordinates of the 2 points C and A. So we just have to extract the x coordinates of C and A and subtract C as the endpoint and then A as the initial point. So the x of C is labeled as x2, okay, the endpoint, and then the initial point x1 or A. So we just have to find the difference, x2 minus x1. So that's the change in x. Okay, because we can only have a line when there's a change in the coordinate. Okay, so we don't have a change in y in discussing the base. We just have the change in x. See, so the y of A and C are equal. Okay, so we just have a change in x. And then here we have the height. Okay, so the height is simply the change in y. So our target point or the end point is B, and the initial point, for example, is C. Okay, so you have the y coordinate of B as y2 and the y coordinate of C as y1. So we just have to find the difference. So y2 minus y1. Okay, and you have the change of y, and the change of y is the height of the triangle. Okay, and we don't have, if we talk about the height, we don't have a change in the x because x2 is equal to x1. Alright, so since we have a triangle, then we can apply the Pythagorean theorem and use that formula, okay, to find the distance. So we have this formula, we just have to calculate, and then finally we get the distance 5. Okay, so that's for this build of green math. So let's proceed to this build, the build of Math Guru. Okay, so basically they have the same framework. So we're going to consider the questions here. Okay, so the first question: what do you observe when these 2 points A and B lie on the same horizontal line? So if they have the same horizontal line like this, so meaning there is no change in y. There's no height, right? The same horizontal line. So we will going to move point B in such a way that point B will be at a line, a horizontal line, the same as the horizontal line of point A. Okay, so we have the hypotenuse here, AB equal to 4.96. So once we make point A be at a line, at the horizontal line, is the same as the horizontal line of point A, like this, then you can say that the base here, CA is equal to 4.04, is now equal to the supposed to be hypotenuse AB, and that is also 4.04. So again, once we move point B to a horizontal line, the same as the horizontal line of point A, the supposed to be hypotenuse AB, okay, is now equal to the base CA. So CA 4.17, and then the supposed to be hypotenuse AB 4.17. Okay, so we don't have a hypotenuse here, we don't have a triangle here, and we just have a change in x. We don't have a height, we don't have a change in y. There's no difference in the y coordinates, but we have a difference, okay, when we subtract the coordinates of the x coordinates of point C or point B. Okay, now the next guiding question here. What do you observe when these 2 points A and B, 2 points A and B will lie in the same vertical line? So we were going to move B in such a way that the line AB or point B will now be at a vertical line the same as the vertical line of point A. So let us observe it together. So there you go. The supposed to be hypotenuse AB, that is equal to 2.83, is now equal to the height BC, that is equal to 2.83. So we have a height. Okay, so now that we have a height, then we have a change in y. We don't have a change of x because the coordinates of A and B at this instance are the same. Okay, so the supposed to be hypotenuse AB, that is equal to 2.83, is equal to the height, the change in y, BC is equal to 2.83. Okay, I hope they found joy in using this GeoGebra build. So it's the build, it's just telling us that in the study of distances, it can be a distance wherein there's a change in y. So if there's a change in y, then you have a height, something like that, in the Cartesian plane. And then if you have a change in x only, then you have the base. Okay, but if the distance has both a change in x and a change in y, then you can have a triangle here. Then we can make use of the Pythagorean theorem. It seems that math is a very elegant topic for the politicians at the time of Mr. President Garfield. Here, we will be talking about one proof of President Garfield. So, President Garfield is the 20th President of the United States that gave this proof or derivation of the Pythagorean formula or the Pythagorean theorem. And this proof was later published in the New England Journal of Education. And the proof is making use of the area or the computation of the area of a right trapezoid in deriving the Pythagorean theorem. So have fun with me learning this classical proof for the Pythagorean theorem that has been presented by President Garfield. And indeed, math is telling us that it is our human nature, okay, to be curious on various math discoveries that shaped the universe. And I also would like to mention that math or a BS math degree is a very good pre-law course or a pre-law college degree because it is in a math college curriculum that you can practice understanding proofs and proving them or presenting them. This is one way for you to master the understanding and presentation of cases. So credit to Mr. Chip Rawlinson for this very good visual for the Garfield's proof of the Pythagorean theorem. So we will going to manipulate the build, okay, so that we can discuss the proof of President Garfield. So let's start by showing the object. So we will start by having the square here, all right, and then if we were going to move it, okay, so as you can see the purple, okay, the position of this point, okay, will somehow give you an idea on how the square has been divided. So in other words, a square can be divided into two trapezoids, okay? And if you don't have any division, then you have a square. And again, if you divide, you can divide the square into two trapezoids. Okay, so let's have this orientation. Okay, a square with two right trapezoids. Okay, so let's start with this line. So this is the formula of the area for a trapezoid. So 1/2 base 1 plus base 2 times the height. So base 1, you have A. Base 2, you have B. So we add this one, A plus B. So we have this. And the height, you have A and the B. So you add this 2 for the height. A plus B. So you have 1/2 A plus B times A plus B. And if we were going to compute this, then we have this equation here. Okay, so let's now describe this line here, this equation. So you have here the area of a trapezoid again, and visually we can see that this area of the trapezoid is basically as the sum of the area of these three triangles here. So we have two yellow triangles and one purple triangle. So we just have to get the area of this triangle, yellow triangle 1, get the area of this yellow triangle 2, get the area of this purple triangle, and add all of them so that we can get the total area of the right trapezoid. That's why we have here area of the 2 yellow triangle plus the area of the purple triangle. So since we are now considering the triangle here, so we'll be making use of the formula for the area of a triangle. So that's why you have here, what is the area of the formula of the area of a triangle? That's 1/2 base height, right? So our height is A, our base is B. So 1/2 AB, that's why you have here. And since we have 2 triangles here, so we have 2 1/2 AB. And then you have 1 purple triangle here. And since we have a square, a purple square, then it was divided into 2. That's why we have here a triangle with 2 sides equal. Okay, so this side C is equal to this side C. That's why the formula for the area of the purple triangle is 1/2 C squared. So C times C is C squared. So we have this line. And now if we're going to simplify these 2 equations here, since we are just pertaining to one area of one trapezoid here, right? So we can equate this equation, this side of the equation here to this side of the equation here. Okay, so that's why we have it here, 1/2 A squared plus 2AB plus B squared. So we bring this down here at the left side of the triangle and equate it to the right side of the triangle, right side of the equation, and that's AB plus 1/2 C squared. Okay, so manipulate this, alright, these 2 sides of the equation, then we are getting the formula of the Pythagorean theorem. And furthermore, we can see in this visual, okay, that the yellow triangles are the right triangles, right? And we can apply the Pythagorean theorem for the right triangles. And upon, again, equating the area of the trapezoid using this derivation here to the second derivation for the area of the trapezoid. So this is formula 1, okay, and then formula 2. And since these 2 formulae are pertaining to one area, and that's the area of the right trapezoid, so we can equate the 2. So equating the 2 and then doing some algebra, then we have the formula of the Pythagorean theorem. And again, this area of the Pythagorean theorem can only be used for right triangles. And in this illustration, the yellow triangles are the right triangles. And indeed, in order to get the dimension of A, B, and C here, then we can make use of this Pythagorean theorem, wherein the blue line here is the A side, okay, A squared, and then B is another side of the right triangle, so you have B squared, and C as the hypotenuse, then that will be C squared. So A squared plus B squared equals C squared. Before we proceed and discuss the details on the standard form of equations for all of the conic sections, let's enjoy a demonstration on how to recreate these instances of conic sections. And this demonstration is just a recreation of the YouTube video that is playing in the background right now. And this YouTube video is telling us that in recreating the instances of conic sections, we just need to have a cone and a plane and have these two surfaces intersect each other, and each intersection of the cone and the plane is an instance of a conic section. It could be in a form of a circle, an ellipse, a hyperbola, or a parabola. And in this math blog, I'm going to share the link of this beautiful YouTube video, and I'm also going to add the link of the Google document that I created that itemizes the steps, okay, for this demo, so that you can also have your own simulations with your learners. Okay, so let's begin. First, we will go to GeoGebra.com or .org. Yeah, .org, .geometry or .org. So let's wait. Okay, and now that we are at GeoGebra.org, then we have signed in. Okay, we'll go to GeoGebra 3D. Okay, for sure we will going to have fun. This is a lot of fun. Okay, so welcome to GeoGebra 3D. So you have here the origin plane, the plane of origin with the point of origin, and then we just go to the pre-built basic tools here. So first we were going to create a cone. So in the steps that I created here, first start with a cone. So we'll have a cone. Some more. Look for the cone. Okay. There you go. And in creating a cone, we just have to start at the bottom point, and then the top point, and then enter the radius. So bottom point, and then top point, and then radius. Define a radius. So radius equal to 3. There you go. We have a cone. And the next step is to move. Let's move to view the cone in 3D. So you just have to click on move here, and then move the cone, so we can have an appreciation on this 3D view. And then the next one, we will going to create a plane, right? So plane with 3 points for this one. And we were going to select points outside the code along the x-axis, y-axis, and z-axis. So meaning this is, for example, the x-axis. So we have to select a point outside 3. Okay, and then for the z-axis, then we're also going to select a point along the z-axis outside 3, and the same goes for the y-axis. Select a point along the y-axis outside the cone. Okay, so let's do that. So I'll choose 6, another 6 here, and 6. Alright, so we have now the plane, and we're going to move for your appreciation. So as you can see, the plane is outside. Alright, so we started in orientation wherein the plane is outside the cone. So let's now simulate or create instances of conic sections by allowing the plane to intersect with the cone. So how to do that? We're just going to move, for example, the point along the z-axis in the plane. So you lower it down. So it's like you're letting the plane to lower down and intersect with the cone. Yeah, okay. So at this point, we have not really view, we don't have lines or yeah, um, a drawing for the intersection, but we can really, we can now see the intersection, right? So we have a command here in GeoGebra 3D where we will really have a drawing for the intersection. So just have to click on select two surfaces and intersect two surfaces and then choose the two surfaces. There you go. Okay, so the instance of intersection, the instance of conic section has now been drawn. Okay, so you have the ellipse here. Alright, and then we were going to move again the point in the z axis, this one, and there. Alright, and then we have the intersection. So move it. Alright, so you have an ellipse here. Okay, so and then you eventually you have a circle, and for better appreciation for this perspective, we can right click on the plane, okay, and then click on create 2D from the plane, okay, and okay, and let me move the camera again. Alright, so you have an ellipse here, and let's move again, and then you have a circle. So moving the point along the x-axis, from outside going to a point along the z-axis inside the phone, then you can create a circle and an ellipse. Now we were going to move the point from a point along the y-axis or the x-axis, so this one. Okay, and moving the point in the y or x-axis will now give you a parabola or hyperbola. Okay. And then move it. Alright. So ellipse, hyperbola, or parabola, triangle. We even have a triangle. Alright, so those are now the instances of conic sections, and each instance of a conic section, circle and ellipse, a hyperbola or parabola, we have quantified it using a standard form of equation, a standard form of expressing a circle, expressing an ellipse, expressing a parabola, and expressing a hyperbola. Okay, so I hope that you have some fun and you gain that curiosity and inspiration to do the same simulation with your learners. So thank you for watching the entire math vlog. So I hope I can write another part about the conic sections. I'll research some GeoGebra builds about the conic sections and study it and discuss those GeoGebra builds with all of you guys. Thanks again.